Hi everyone, this is Shuilin Tian. Today I will introduce you a unified equivalent circuit model of V-square control, which is also applicable to ripple-based control. The equivalent circuit model can predict all transfer functions very accurately up to half of switching frequency. The equivalent circuit model is applicable to all kinds of capacitors and also to different schemes such as constant on-time V-square control and constant frequency V-square control. Hopefully, this model will serve as a powerful tool for designing and understanding purpose. First, let me give a brief introduction of V-square control. The output voltage is fed back and used twice. One through a direct feedback without any compensation, and the other comes through a simple integrator to provide control signal. In many applications, the out-loop integrator can also be saved, which is called ripple-based control. This structure is very simple and provides very fast transient response. It is widely used in industry. Many products employ constant on-time V-square control or constant frequency V-square control schemes. The issue for this structure is that the stability is related with capacitor parameters, as the output voltage contains ESR ripple and capacitor voltage ripple. For large ESR caps, such as Oscon caps, ESR ripple is dominant and the structure is elegant. However, for small ESR caps such as ceramic caps, capacitor voltage feedback is strong and instability is observed. Industry products use additional inductor current to stabilize the circuit. Alternatively, capacitor companies such as TDK provide some series of controlled ESR ceramic caps, letting customers customize ESR to stabilize the circuit. For understanding and designing purpose, it is wonderful if we can develop a small signal equivalent circuit model. In this graph, the output voltage is separated into inductor current feedback, capacitor voltage feedback, and load current feedback. The new challenge for modeling V-square control is that not only inductor current ripple participate in modulation, but also the capacitor voltage ripple. As a result, if there is a modulation on control signal, not only the sidebands of inductor current loop needs to be considered, but also the sidebands of capacitor voltage loop. Up to now, there is no equivalent circuit model taking capacitor voltage sideband into consideration. From the describing function result, the capacitor voltage feedback causes a pair of double pole at half of switching frequency. From the body plot, we can see that the gain is 1 at low frequency, which means that the output voltage can well follow the control signal at low frequency. At half of the switching frequency, there is a double pole. Physically, it means that the capacitor voltage feedback turns the circuit into a non-ideal voltage source. Our proposed equivalent circuit model is based on the previous non-ideal voltage source concept. From knowledge of current mode control, the inductor current is well controlled by control signal Vc2. For V-square control, Vc2 is composed by Vc1, Vcap Fm, and sideband of the capacitor voltage Vcap Fsw-Fm. And this shows our proposed equivalent circuit model. Vc1 Fm is responsible for the red control source, and the modulation frequency of capacitor voltage Vcap Fm is represented by a resistor RCO. By Thevenin's theorem, we can see that this resistor basically turns the current source into a voltage source. The sideband frequency component Vcap Fsw-Fm is represented by an inductor Le2 in series with a resistor Re2, which represents the non-ideal voltage source, as Le2 and Re2 will form the double pole at half of switching frequency by resonating with output capacitor. Le2 determines the double pole position, and Re2 is related with the damping of this double pole. Therefore, this simple equivalent circuit shows that the capacitor voltage feedback turns the current source into the non-ideal voltage source. Now, for a general case, the inductor current sideband information also needs to be considered. This graph shows the equivalent circuit. The equivalent circuit reveals that the inductor current feedback turns the power stage into a non-ideal current source. The non-idealness of this current source is shown in equivalent circuit by resonance between CE and LS. The capacitor voltage feedback turns the current source into a non-ideal voltage source. The non-idealness of this voltage source is shown by resonance between LE2 and output cap CO. Now, by considering the input property as the same way in current mode control, we can get the complete equivalent circuit model, and this model can be used to derive all the transfer functions. This shows simulation verification for OSCON capacitors. The control to output voltage, audio accessibility, output impedance, and input impedance are compared. We can see that the proposed equivalent circuit model agrees with simulation results very well up to half of switching frequency for all 4 transfer functions. And this shows simulation verification for a 2-phase constant on-time V-square control with ceramic capacitors. Again, the proposed model can predict the double pole at half of switching frequency very accurately, and it agrees with simulation results very well for all 4 transfer functions. This shows simulation verification of control to output voltage transfer function for constant frequency V-square control. For both cases using OSCON capacitors and ceramic capacitors, the control to output voltage can be designed as a flat gain up to very high frequency. We can see the model agrees well with simulation results up to half of switching frequency. This is the experimental waveform based on LM34930 demo board with traditional 10 micro ceramic caps, which has a small ESR around 5 milliohm. We can observe that there is an instability problem, which is predicted from our model as the system has a right half-plane double pole. Now use the customized ESR ceramic caps, which has around 50 milliohm ESR. We can see the circuit is stable, which is predicted from our model as the system now has a left half-plane double pole. Now we do the measurement of control to output transfer function to verify our model. The measurement is based on network analyzer Angeland 4395A, and this shows the measured transfer function. We can export the measurement data and compare with the equivalent circuit model. We can see that the prediction from equivalent circuit model can match well with the experimental data up to half of switching frequency. That's all for this video. If you have any questions or comments, please feel free to discuss with me. Thank you.